Good morning, everyone. My name is Aina Clara Binti Bahari, and my medical number is 103142. This is my team member, Aina Hanum, Naikachi Chashonshan, and Lee. So, our team is excited to present our operating system project focusing on CPU scheduling solution. Okay, to begin, I will discuss our methodology and how we'll present the processes in our system. We utilize a process control to store essential details for every process and ensuring proper management during execution. So there is a few key data points in our procedure, which is process ID, unique identifier, then arrival and reverse time when the process enters and the specific time it needs, and then time management metrics such as remaining burst time, finish time, turnaround time, and waiting. All the processes that are ready for execution are held in a ready queue. A process enters this queue as soon as the system clock reach its specific arrival time. This structure allows us to track every microsecond of the simulation accurately.
Moving on to our next topic, which is the scheduling logic. We implemented the round robin algorithm. In this model, the CPU executes each process for a fixed period called a time quantum. If a process isn't finished when the quantum expires, it is moved to the back of the queue to wait for its next turn. A critical factor in our simulation is the context switch delay. We applied a 1.0 ms penalty for every switch between processes. This represents the real-world overhead required for an OS to save and load process states. To manage this, we use a global clock. This clock tracks the running time, CPU work, switching time, the overhead, and idle time, which is when no processes are ready. This ensures our simulation accounts for every millisecond of system activity.
Hello, my name is Sasha. I will now walk you through the implementation. We wrote our simulation in Python, use a process class to act as our PCB. To ensure our results were accurate, we use standard OS formulas. The finish time is recorded the moment a process completes, which then allow us to calculate turnaround time, the total time from arrive to finish, and waiting time. As you can see from our terminal output, we test three specific scenarios: 3 milliseconds, 10 milliseconds, and 25 millisecond quarter. For each run, we track the total number of contacts, switches, and the resulting overhead. The data on this table summarize our simulation's performance. At a 3 milliseconds quantum, we saw a massive 990 context switch, leading to 990 milliseconds of overhead. When we increase the quantum to 10 milliseconds, those switches drop significantly to 327. Finally, at 25 milliseconds, we achieved the lowest waiting time of 2031.87 milliseconds because we only have 165 contacts switch.
Hi, my name is Ling Yi. Now let's examine the data generated by our simulations. Our charts clearly illustrate a critical inverse relationships between the time constants and the system overhead. If we look at the specific performance metric at 2 minutes, we have the higher waiting time that are 2680.88 minutes due to 990 contact switches. This creates a massive 990 minutes overhead, meaning the CPU is too busy to switching instead of walking. At 10 minutes, performance improved significantly. Waiting time dropped to 2,167.61 minutes and switch reduced to 327. At 25 minutes, we see the best efficiency. Waiting time is only 2,031.87 minutes with just 165 switches, cutting overhead to 165 minutes. Looking at the figure 1 and 2, we can see how the step visible drop in both turnarounds and waiting time as the quantities increase. Figure 3 highlight the contextual overhead, which plunges from near 1,000 minutes down to 165 minutes. In conclusion, this result proves that the larger quantities increase row efficiency by minimizing the penalty of frequency content switching. However, as we will see in the next session, efficiency is not the only factor we must consider.
I will present the optimization conclusion for our project. To conclude, our simulation revealed a classic trick of operating system. While the 25 millisecond quantum achieved the best raw performance metric due to the minimal overhead, it carried a hidden cost. A very large quantum causes the system to behave like first come first serve. This reduces fairness and makes the system less responsive for the shortened tasks. Conversely, the 3 millisecond quantum is highly inefficient because it suffers from excessive context switch overhead. We have determined that the 10 millisecond quantum is the most suitable choice for this system. It provides a practical balance, it's efficient enough to keep overhead low, but in short enough to maintain the round robin benefit for responsive and fairness. That's conclude our presentation. Thank you.